A continuous 240-volt mains power alternating current solenoid with a long bolt placed within can also levitate a ring and demonstrate in a simple way eddy current levitation. The mains power provides sufficient amplitude. In a similar way, 4 electromagnets set at a geometry of 90 degrees apart can produce a magnetic force on an aluminium disc that will balance the levitator. Lateral stable levitation can also be achieved by 2 concentrically but oppositely wound coils. A single coil will also levitate an aluminium disc but would require a pivot for stability, otherwise the disc will slide off. The electromagnets generate a changing magnetic field which induces an EMF, forming eddy currents within the plate. No, not a flux capacitor, but 2 flat pancake coils that are also wound oppositely, but this time powered by a high frequency alternating current of 44 kHz of 105 watts, commonly available as an electronic low voltage lighting transformer. A conductor can be levitated above an electromagnet with low frequency alternating currents just as well with an air core pancake coil with higher frequencies. This method achieves a very stable but undampened equilibrium without any need for feedback control such as method 10. The copper coil is energized with 240-volt 50Hz AC mains power, which provides sufficient amplitude, and by adjusting the voltage amplitude, the levitation height can also be adjusted. We can also use high-frequency excitation, where the incident magnetic field is shielded from passing through the plate. This is due to large induced circulating currents in the plate. In this case, the flux lines are compressed beneath the coil. The resultant induced currents may be used to generate a lift force as in a maglev, or may be used to heat the conducting plate as induction heating. A simple calculation can determine the minimum plate thickness at a given operating frequency to reach the high frequency limit. Using Fleming's left-hand rule for electric motors shows the direction of the thrust on the conductor carrying a current in the magnetic field. Therefore, different geometries of coils can be used to levitate different geometries of metal objects. The one shown is a common induction motor commonly found in fans and old record players that had the top half of its laminations cut off. This low energy device just levitates and rotates an aluminium cylinder. Greater electrical power and additional phases with corresponding conductor geometries achieve far more stable levitation at increased heights. In the case of low frequency excitation, where the operating frequency is sufficiently low, the induced magnetic field due to induced currents is small compared to the incident field. The magnetic field of a pair of identical coils with their axes along a vertical line are separated by a distance comparable to their diameter. When the currents in the coils flow in opposite directions, a cusp-shaped field is produced in which the magnetic field is zero at the center point between the coils. This magnetic field is capable of supporting stably and centrally an aluminium cylinder, executing remarkable gyrations and oscillations if set into motion. Higher frequencies in the RF band can also be used with a pair of coils oppositely wound as in the previous method. With sufficient power from 1 kilowatts, this technique will even suspend small quantities of electrically conductive material and even melt the material by induction heating. As discussed in method 11, Faraday's law together with Ampere's law and Ohm's law is Lenz's law. Nikola Tesla demonstrated his induction motor system and used the device he called the egg of Columbus. The egg spins on its major axis standing on end due to gyroscopic action. This demonstrates that the induction motor does not require any connecting wires in the rotor and is a brushless motor and has been used quite commonly for over 100 years. Cross-section shows a modern induction motor based on Tesla's principles. A simpler version can be made using a small induction motor that operates with a single phase of common mains power. The inner rotor is removed, the porcelain crucible placed within, and a half dome of hollow aluminium rotates within without any physical connection. Or an even smaller gear reduction drive induction motor coil with a crucible rig placed over it, where a small magnet is embedded within the aluminium board, which rotates wildly at 3000 RPM or 50 Hz. The next experiment shows a similar principle called a perpetual spinning top. The top is made of an insulator such as plastic and contains a small permanent magnet orientated perpendicular to the spin axis of the top. The base contains a transistor and a coil with 2 windings, driven by 9-volt power supply. When this coil is switched off, the rate of fall through the cavity is as one would expect. When the coils are energized with an alternating current, a time-varying magnetic field is induced around an aluminium conductor, reducing its rate of fall. This demonstrates that a moving magnet that has relative motion to a non-ferrous substance with method 11 behaves in a similar way to a time-varying magnetic field generating by a time-varying current, such as alternating currents or AC. Here we have 4 non-ferrous metal conductors, therefore as shown, do not normally attract a magnet. From the viewer's left, a closed aluminium ring, next an aluminium ring with a slit cut vertically, therefore open circuit, a simple coil of copper wire that is first tested open circuit, then tested closed circuit, and on the far right a metal tube. When the rod magnet is pulled away quickly from within the rings, levitation via a magnetic attraction is achieved, with exception of the ring with a slit and the coil left open circuit. Both open circuit coil and ring do not attract the magnet to the degree of the closed circuit, as greater currents are prevented from flowing. The simple experiment showed that if we raise a magnet away from a conducting loop of wire, the movement of the magnet generates a current through the loop in this direction, and that it opposes the change of the magnetic field in the upward direction, then the coil will produce the magnetic field in the opposing direction, attracting the magnet. If we reverse the situation and push the magnets towards the coil, the current will reverse in the loop and the magnetic field repelling the magnets. This is shown in the next experiment, demonstrating that a magnet can push a ring of non-ferrous aluminium away by relative motion, and that the effect is also reduced when the ring is open circuit. We can use this general principle to create levitation or negative gravity that generally pushes conductors away, but can also be made stable by various means other than pivoting or tethering, which we'll discuss. As in our previous experiment, we can induce this relative motion by a magnetic field using the oscillatory decaying nature of the spark discharge, derived from a discharge of high voltage capacitors charged with a high voltage direct current.
This powerful force will be utilized in the construction of a magnetic pulse propulsion device. The propulsion being the effect of induced currents in a metallic ring by that of an electromagnet that will act in opposition to the change in magnetic flux that was originally generated, or eddy current flow, where an aluminium ring can be propelled into the air up to several hundred feet. This force is demonstrated by the magnetic and mechanical reaction produced by the Lorentz force. We see that energy in the form of the electromagnetic pulse produced by the electromagnet. The demonstration model you will see can project an aluminium ring at velocities of several hundred meters per second.
10-volt charge. How much power? 30-volt charge.
Capacitors are charged to 700 volts. T minus 4, 3, 2,